Okay, so today I had a couple things I wanted to go over with rotational kinematics. I know you guys had some questions on those problems. So I thought let's start out by really going back over our theta, omega, and alpha and what those really are, okay? So a theta is an angular position. It's just basically where you are at. It's kind of like your x equivalent, but for rotational motion. So if we go take a look at the wheel again, right? If you've got a dot on the wheel, let me see if I can get zoomed in here so you can see a little better. Yeah. Okay, so there's my dot. If I want to know where it is right now, well, the way I have to describe that is in terms of theta, right? So I have to describe it in terms of like basically how many radians it's gone through, okay? So from here to there, it's gone pi over 2 radians, okay? A little bit farther, it's gone pi radians, a little bit more, 3 pi over 2, and then back to 2 pi radians or a full cycle, right? One full circle. So if I want to figure out basically where I'm at, I have to use theta. I have to figure out how many radians I've gone through, okay? Rotational or angular acceleration, angular velocity, right? Those things have to do with basically how fast the wheel is going around. So if I want to go faster, again, I'll have some kind of a set speed like this, and you can kind of see the dot a little bit on there. You can kind of mark how many radians it's gone through per second. Angular acceleration, if I'm going at some speed and I speed it up, then I've accelerated and I'm going through more and more and more radians per second. So, but let's take a look at how that relates back to linear stuff real quick. Okay, so if I want to get, that's a position, isn't it? Sure, at that dot, I've gone through so many radians to get up to here. But I've also covered an arc length. I've actually covered that length distance. So if I want to know what that arc length actually is, I can do that, and it's pretty easy to figure out. So what you need is figure out how many radians you've gone through, right? And it turns out if you want to know your x position, and really I shouldn't call it x, I should call it my arc length, which usually they call s, okay? I'm still going to call it x because it's just a distance we've covered, right? So if I want to know the distance that's been covered by that dot as it spun around on the wheel, what I need to know is basically how many radians I've gone through and how far out from the center it was. So number of radians you've gone through times your radius will actually get you your arc length or your distance covered by that dot or wherever you're at on the wheel. Okay? So there's kind of an easy relationship. Anytime you want to get to a linear variable, okay, the linear version of it, all you have to do is take the rotational version and multiply it by the radius. And that's it. You'll actually get straight back to your linear variable. So let's check this out. Angular velocity. Okay, first off, I had a question. Why does it say angular velocity instead of angular speed, vice versa? Like, is there a difference? Yes, there is. Take your right hand, okay? Your right hand, you're going to take and curl it around in the direction that the wheel goes, okay? So if the wheel is going this way, I would curl my fingers in this direction. You see which direction my thumb is pointing? It's pointing towards you, right? So that means I have, because it's going counterclockwise, right? I'm getting a positive angular velocity out of it. If I were to go the other direction, my right hand rule would say I curl my fingers in the direction the wheel is going, and you'll see my thumb will actually point away from you into the board, right? So that would be a negative direction for angular velocity. So just to clear that up, okay, angular velocity, if you're going this way, it's positive. If you're going that way, it is negative. Okay, that's generally the convention that people follow, right hand rule. Okay. What if I wanted to get my velocity from this? Well, again, I'd have to know, if I want to know my linear velocity, I'd have to know how fast around I'm going, and I need to know distance away from the center. Okay. An angular acceleration. So angular acceleration, what that is, or tangential acceleration, if I'm going around like this, the tangential acceleration, all of these variables are the thing that happens at that tangent to that point, right? It's going to be on the outside of a circle, or if it's some distance in, it's not a full radius length away, right? Well, it's still going to make a circular change here, right? You're still going to have a tangential velocity, right? Tangential velocity, tangential position, or really an arc length, right? Or a tangential acceleration, how fast am I speeding up on that edge, okay? So if I want to know my A tangential, okay, on the outside of the circle, what's my acceleration? Well, same thing applies. If I'm speeding up how fast I'm going around, right, faster and faster, I have an alpha, okay? I have an angular acceleration. And just like this, it can have a positive, right, curling around this way, counterclockwise, positive angular acceleration, or it could be a negative, right? So on this one, if I want to find my tangential velocity, I simply multiply that angular acceleration that it's experiencing and how far out it is from the center point, right? Its radius. And that right there will get you to your straight line, your linear variable from your rotational, okay? So let's go ahead and solve a couple problems. I know you guys had a couple questions on number 2, and then on to number 6. It had an issue with the time on it. I think I'm actually going to leave, I'll work out number 6 here too. And so number 2 basically was asking about, you have 2 people, 2 kids, right, on a merry-go-round. One's out at the edge and one's on the interior. I think that's how it went. Marilyn and Sheila there. Okay, so yeah, number 2, I had Marilyn was on the outside, Sheila was on the inside. Okay, and it wants to know, okay, one is halfway, so there's the center point, okay, so it's all rotating around that center, okay. Everything's going around the center of the merry-go-round, which is important. They're not rotating about this point, right? It makes a difference, okay. And then this radius here is 1/2 of r, and this one here is just r out to Maryland, okay. So it wants to know, what is the relationship between the centripetal acceleration and the 2 sisters? Well, centripetal acceleration is going to be basically the centripetal acceleration, if you remember, is v squared over r, or omega squared times r, okay? So you can imagine, as you're farther out on this wheel, right, you've got a higher v, even though your angular velocity stays the same. So as your r increases, right, even if you've got the same omega out here, everybody's traveling the same number of radians per second, the farther you go out, you're covering more distance, so you've got a higher centripetal acceleration. Closer you are to the center, the lower your centripetal acceleration, okay? So if you're closer to the center, you're actually feeling less of a push, right, in or out, centripetal or centrifugal, right? If you're on the outside, you're feeling more, okay? So for number 6, going straight into that one, we got a wheel and it's spinning around, okay? So if you have a wheel spinning around for number 6, it's got a couple things it wants to know. So for 6, there's actually 2 ways to solve it, okay? I can use one of 2 things. I can do a timeless equation. Omega final squared is equal to omega initial squared plus 2 alpha times your distance, right, is what we would have called it before, so we'll call it theta now, okay? So if that's what you got, look at how this relates back. And how did I get that? I got that from our timeless equation last semester. The initial squared plus 2AD. Distance we've covered, number of radians we've gone through. Alpha, angular velocity instead of our angular acceleration instead of our acceleration. I have an omega instead of a v, right, for my initial and for my final. So that's really how I got to this timeless equation. So I can solve number 6 that way, or if I want to know a final omega, I can also just use my omega final equation, which is this. See, I'm trying to go linear here. Okay, so alpha t, and you can see how that's similar to my v final equation from last semester, right? Very similar. Pretty much the exact same thing, except for I'm putting in rotational terms instead. So either way you can solve this problem if you want to get to an omega final, okay? What you know is that it starts from rest, okay? So omega initial is equal to 0, okay? And you know that it has an angle at the beginning. Theta initial is 0, okay? And it has a constant angular acceleration, so it has a constant alpha, and that alpha is -4, and this is radians per second squared. Omega, of course, is radians per second, and this is just radians for your theta, right? Okay, so, and it has a time also. Another important thing, it gives us time. T is equal to 5.245, seconds. Okay. So how in the heck are we going to now find the angular velocity for the wheel after time. So how are we going to find omega final? Well, we got two equations we could possibly use, right? This is the simpler one. Since you have time, I'd go with this, right? You have everything in there you need. If you didn't have time, if you had the number of radians that you went through, I'd use this one, okay? And again, if you don't have time, the equation you have to use is timeless, okay? So since I'm going to use this one, I'll just show you this one. You guys can probably work through that one on your own if you want to, okay? Since I'm going to use this one, though, what we need is we know our initial speed, right? Our initial velocity is 0. We know our alpha is -4. We know our time is 5.245 seconds. Okay, so when I do this, I basically will get 20 and a bit, right? And if I multiply 4 by 5, I'll get a negative speed, so it won't be turning this way with your thumb towards you, it'll be turning this way with your thumb away from you, right? It'll be going clockwise. So you get a negative 20, I think it's 0.98, I think is what you get, radians per second. So that's really all you have to do for number 6, okay? Number 9, A and B, I had a question on also, so I'll go ahead and go over that one, okay? Okay, so probably a similar, if I remember right, working this one before, I think it was a similar equation. So we had 9A. Okay, so 9A is asking about a CD that's going. Okay, so you got a CD here. It starts out at rest. Okay, so its omega is 0 at the beginning. Okay, and later on, it has an omega, and it is going, it says positive, right? So I'm going to assume my omega is in this direction. My omega final is 399, and this is important. RPM means revolutions per minute. That's not our standard unit, is it? Okay, so we're going to hold on to that for a moment. We'll come back to that, okay? So we also know our time. We know time that this is going to happen for is 3.3 seconds, okay? And we want to know, what we want to find out, the main thing here is our alpha, or our angular acceleration. That's what we want to find, and our units are going to be radians per second squared, okay? So radians per second squared, we got seconds here, we have revolutions per minutes here. We got to get that to radians per second to start out with, okay? So the first step on this is actually railroad tracks, the dimensional analysis. So we need to get 399 revolutions per 1 minute, and we need to get it into radians per second. Okay, so what we need to know is how many revolutions, how many radians are there per 1 revolution? Revolutions are on top, so revolutions have to go on the bottom. So we know 1 revolution is 2 pi radians. Revolutions now cancel out, so we are on our way now, right? We'll get radians per minute now, right? We got to get out of minutes, okay? So minutes have to go on top to get them to cancel. We know 1 minute is 60 seconds, okay? So I'm going to have to work this out on my calculator because this is too much math for me to do in my mind right now, but basically this will be not quite 800. What is that? It's going to be 798 radians. And I see I was being lazy. I forgot to cancel out my minutes there. Over some number of seconds, over 60 seconds, right? So 798 divided by 60. Walk through it with me here. You guys can do this at home, right? But we get 798 divided by 60. We get 13.3. 798 pi radians. See, forgot the pi in there. That also has to carry through. 798 pi radians over 60 seconds is 13.3 pi radians per second. You can multiply by pi right now if you want to. But I've got my omega. Okay, that is now my omega final. Okay, so that's also equal to 13.3 pi radians per second. Okay, that's my omega final. And I want to find my alpha. So again, look at what we've got. We've got initial and final velocity. Okay, we want to find an acceleration, and we know time. So the best equation was one of those ones that we used before. So what we want to do is we want to use omega final is equal to omega initial plus alpha times time. Okay, so we know this value, 13.3 pi. We know this one is 0. We know this We don't know that, do we? That's what we wanted to find. Alpha, okay, but we do know time. Time is 3.3 seconds. 3.3 times 3.3 seconds, okay? So now we need to rearrange that to solve for alpha. Well, okay, 0 goes away, so we don't have to worry about it. So we get 13.3 pi divided by 3.3 seconds, right? That's radians on top. And we will get our alpha. Work it out and you will be able to find the correct answer, okay? 9b, see where we're at here. Okay, 9b, CD is reputed, so it's the exact same thing. So we still have these terms. So we still have the same problem, but we want to know how many radians it goes through, okay? So if you want to know radians, okay, the one thing that you will actually be able to use to find radians, well, there's two, okay? You could do, if you do the timeless equation, this is the less obvious one to use, right? You could find your number of radians that you went through, okay? Totally works, nothing wrong with that one, okay? The other one you could use is your final radial position equation. Theta final is equal to theta initial plus omega initial times your time plus 1/2 alpha times squared. Well, either one will work, okay? I'm going to go ahead and use this one because that's kind of, when you think about trying to find theta, that's probably the best way of going about it, okay? So, I'm going to use this guy, so let's plug in what we got. It says that we start from rest. We're not given an initial position, so we have to assume. If we're going to assume, we assume 0, okay? 0 radians to start out with. We want to find our theta final, okay? Omega initial, we said was at rest to start out with, so that's 0, okay? So we got 2 zeros. Yay, makes it easy, right? So all we have to do then is 1/2 times our alpha, which we know our alpha now, we just found it, and that is, what did we find for our alpha? Well, we found it in the last problem, so you can use it here. It ended up being 13.3 pi over 3.3 seconds, right? And then times your time, which is 3.3 seconds. But this one has to be squared, okay? You got to square that term. So one of your 3.3s, kind of cutting off there, okay? One of your 3.3s here is going to basically cancel out, okay? Because you got on the bottom here, and you got 2 of them over there, 3.3 times 3.3, right? So you'll end up with 1/2, theta final is equal to 1/2 times 13.3 pi radians times, where seconds was squared, now it's just seconds, right, times 3.3 seconds, right? And now seconds will cancel out, so you'll end up with radians per your unit. So multiply that out, 1/2 times 13.3 pi times 3.3, you get your final position, and you're done, okay? I'll record a separate video for number 10, that was the extra credit anyway, so you guys don't get overwhelmed, it's already 18 minutes long. Okay, so there you go.